When COVID-19 cases started to grow exponentially, people everywhere scrambled to figure out how to use their skills to make a difference in this global crisis. For 4 of my team members, students at McGill, the publication of the Code Life Challenge sparked a realization. They could help with the COVID crisis by designing and building a ventilator. The initial group of 4 students quickly expanded to a diverse group of 14 passionate Canadians. We wanted to focus on using only open source technologies and widely available and manufacturable parts, while still maintaining the medical precision and reliability required of a device as life-saving as a mechanical ventilator, and at moderate cost. That's what we've done with our ventilator. Breeze. But how to design such a ventilator? One popular design possibility was quickly set aside: piston squishers, because the bags they squish are not readily available, and reciprocating parts are very prone to failure over time. This led us to the possibility of a blower system with, at its core, a fan pushing air at a specific pressure into the patient's lungs. But most such systems rely on a number of fragile mechanical parts, which are hard to obtain and manufacture. We realized that we could avoid this fragility if we could design a blower system which used minimal mechanical parts, relying instead on passive valves and software. We knew that we could do this, and we also knew that we could design and 3D print critical parts ourselves, meaning we didn't have to rely on third-party manufacturers for things like turbines. This is our ventilator design. Air and oxygen are fed as the inputs to a 3D printed turbine, run with an off-the-shelf motor. The pressurized air coming out of the turbine passes through a series of cleverly designed passive valves on its way to the patient. Let's dive in a little deeper on our design to see how all of the components come together. Limitations in resources have led to mechanical ventilator access restrictions based on equipment and personnel availability. We hope to help on both fronts. Not only did we want to make our ventilator be easy and accessible to make, but we wanted to facilitate its use by less experienced operators for COVID patients. With this in mind, we designed an intuitive touchscreen interface with recommended parameter ranges for COVID-19 patients, smart alarm triggering, and automated system tests. To simplify our system, a microcontroller is used to control all electronic components, allowing adjustments of ventilatory mode, pressure control and pressure support, and, when relevant, respiratory rate, inspiratory time, and other standard ventilation parameters. To achieve the required high oxygen, or FiO2 values, 2 intakes provide inspired gas admixture on our device, 1 for air and 1 for oxygen. We control these by opening either a butterfly valve or a needle valve, operated with a servo and a stepper motor respectively. The combined air and oxygen goes into the heart of our ventilator, our turbine. Our turbine is custom designed for delivering pressure-driven respiratory support. It's spun with an off-the-shelf motor controlled by the Arduino to achieve appropriate pressure values. To limit maximum airway pressure, we pass the pressurized air through a mechanical fail-safe valve. We also have an emergency check valve to allow airflow to the patient in the case of catastrophic failure of our turbine. To calculate tidal volume, the air then passes through a flow sensor connected to the Arduino. We also use this sensor for flow-triggered breaths. To prevent rebreathing, the air passes through a simple check valve which isolates the internal system from the patient-connected system. To control circuit humidity and temperature, the air then passes through an HME before entering the patient. Because COVID-19 patients often require high PEEP values, we designed a valve which, controlled by the compressor, allows us to set a fairly broad range for the PEEP. So, to recap, air and oxygen come in through our valves, are pressurized by our turbine, pass into the patient, and out through our PEEP valve and exhaust. With only 3 active components, we're able to deliver precise ventilation through clever valve and software design. But things go wrong in the real world, and we've thought about that. If power fails, we have a built-in internal battery, which will maintain ventilator operation for 20 minutes. Our design includes the ability to connect and hot swap any external 12-volt battery, and we have a built-in battery management circuit, which will charge and maintain our internal battery. If disconnections occur on the electronic side, or we detect sensor failure, alarms connected to both the Raspberry Pi and the Arduino will sound. When it comes to infection control, the device is designed to be cleaned easily and rapidly to accommodate the ever-growing number of COVID cases. Its exterior is made of acrylic and most surfaces are sealed, so it can be cleaned with standard disinfectants. In between patients, the entire patient circuit needs to be swapped: the HME, tubing, and Y connector. These components are medically standard, allowing our device to be readily deployable. To prevent contaminated air from being inhaled or exhaled by the patient, we've designed custom quick-swap filter housings which hold standard HEPA filters and are located at all intakes and exhausts. These housings can be readily disinfected or replaced. Because the inside of the device is isolated behind multiple filters and check valves, it does not require sanitation between patients. And that's our design. In only a few weeks, we've been able to make a ventilator design capable of delivering precise and reliable ventilation to COVID-19 patients with only 3 active components. All of the components in our design are readily available or 3D printable, and the software we wrote for it can be used intuitively by inexperienced operators. This makes our design ideal to be used for the COVID-19 crisis. Our team is very proud of what we've been able to pull off in the past few weeks, but we wouldn't have been able to do it without help from many people, so thank you.